The Thai Research Reactor. The Thai Research Reactor began its operation in 1960 after the Thai cabinet agreed that the Thai Atomic Energy Commission would have the Thai Research Reactor building constructed in the Bangkhaen area. Later, in April of 1962, Field Marshal Saret Thanarat, the Prime Minister at the time, laid the foundation stone of the building and named the research reactor Thai Research Reactor 1, or TRR-1. In 1962, groups of scientists, engineers, and mechanics loaded the fuel into the reactor core, and the TRR-1 achieved criticality for the first time in Thailand that year. After Thailand had signed the Nuclear Non-Proliferation Treaty in 1972, in order to comply with the regulations in the treaty, the previous reactor core with approximately 90% enrichment fuel was converted into the new reactor core with approximately 20% enrichment fuel. The core of the new reactor became the Trigger Mark III type, which was designed and made by the General Atomics Company in the USA. After the modification, the Thai Research Reactor 1 was renamed the Thai Research Reactor 1 Modification 1, or TRR-1-M1. The major components of the TRR-1-M1 are 1. The reactor core. 2. The cooling system. 3. The instrumentation and control system. And 4. Shielding. Now the details of these 4 components. First, the reactor core. The shell of the reactor core is an aluminum cylinder 55 centimeters in diameter. Inside the cylinder there are 2 aluminum plates. One is at the top, the other is at the bottom. The upper plate consists of 121 holes, like a honeycomb, which is used as the fuel rod guide. Also, the inner part of the reactor core contains an americium-beryllium neutron source, of which the neutron intensity is approximately 3 curies. Fuel rods. The fuel rods of the reactor core are about 90 centimeters long, filled in stainless steel claddings. Inside each rod is uranium zirconium hydride fuel. Control rods. The TRR-1-M1 contains 5 control rods, which are used for controlling the chain reaction. 4 of them are fuel follower control rods, and the other is an air follower control rod. All the 5 control rods contain boron carbide on top of the rods, acting as the neutron absorber. The fuel follower control rods contain fuel meat in the bottom part, while the air is filled in the bottom for the air follower one. An operator controls the reactor power by pressing the up or down buttons one by one until the desired power is obtained. Neutron detectors. The neutron detectors measure the amount of neutrons produced by chain reactions, which indicates the reactor power. Second, the cooling system. During the reactor operation, the water in the pool around the reactor core, heated by the core, rises to the surface. Then it is pumped out of the reactor pool to the 2 heat exchangers, where heat is transferred to the water in the secondary system. After the water is cooled, it is brought back through the lower pipes of the reactor pool. The water in the secondary system is brought back into the heat exchanger system after it has passed through the cooling towers. Also, the water treatment system removes contaminants from the pool water by passing the water through resin. The third major component is the instrumentation and control system. The instrumentation and control system displays the values of important parameters of the reactor, such as water temperature, fuel temperature, reactor power, and so on. 5 staff members are in charge when operating the TRR-1M1, 1 supervisor, 3 operators, and 1 health physicist who is responsible for radiation safety. And 4th is shielding. The water in the pool is approximately 8 meters deep. The thickest part of the concrete wall is 1.35 meters. Shielding allows the staff to operate the reactor safely. The irradiation facilities of the TRR-1M1 are classified into 2 types. First, the in-core irradiation facility, and second, the out-core irradiation facility. The in-core irradiation facility is a long tube of which the top is shaped like the bottom of a funnel. It is called the irradiation tube, and it is fixed inside the reactor core. The outcore facility can be further classified into 5 types. First, the wet tube, which is a movable aluminum irradiation facility, having a semicircular shape. At the top of the tube are 5 holes for inserting topaz containers to be irradiated. Second, the tube in void tank VNVS, which is another type of wet tube. It is an aluminum rod fixed to the wall. At the top of the tube, there are 2 holes for inserting topaz containers to be irradiated. Third, the dry tubes CA2, CA3, TA, A4, A1, and TC, which are 6 long tubes fixed to the reactor bridge and next to the reactor core. They are usually used for irradiating samples for the neutron activation analysis technique. Fourth, the rotary irradiation facility, or Lazy Susan, which is an aluminum irradiation facility with a donut shape, fixed to the outside of the reactor core. And fifth, the sniff irradiation facility, which is an aluminum cylinder with a long core stretched up from the upper part of the pool. It is alternately operated with the wet tube. Neutron beam tubes. The 4 neutron beam tubes are made of aluminum and fixed on the side of the reactor pool. They lead neutrons for experiment work outside the pool, such as neutron radiography, or PGN-AA, also known as prompt gamma neutron activation analysis. Uses of the TRR-1M1. The neutron particles from the TRR-1M1 can be utilized for 1. Irradiating stable isotopes to produce radioisotopes, which are useful for medicine, agriculture, and industry. 2. Enhancing the values of gemstones. When irradiated in the reactor, natural gemstones change their colors, such as from white topaz to blue topaz. Their values are increased by 5 to 30 times. 3. Neutron activation analysis, or NAA, such as analyses of heavy metal in wastewater before drainage into the environment, and archaeological dating. 4. Research and development that require the reactor, such as research and development on micropore membranes. 5. Neutron radiography, which refers to photographing the inner parts of samples without destroying the samples. 6. Training in science and nuclear technology. TINT also provides knowledge of the research reactor to students and teachers at schools, colleges, and universities. In order to promote science and nuclear technology, experiments with the reactor are available. And 7. Public relations work in order to create public understanding of the necessity, usefulness, and safety of the research reactor. It is a pleasure for the TINT to welcome all of our visitors to the TRR-1M1, and we thank you for joining us today.